continuation of our lecture on small molecules. This is Small Molecules Part 2, and we're going to be talking about the properties of water. Water makes up a huge, huge part of both living organisms and our planet. And there's some very deliberate reasons why that's true. Water has some amazing properties to it that make it a very good solvent. Meaning that it dissolves things well. It also has some properties to it such as having a high amount of heat index, or has an ability to take on a lot of heat before it boils off in a gas, which is good because you wouldn't want to go outside to get a suntan and boil away. So it also has some other unique properties relating to its freezing properties that we probably won't have time to get into. I want to cover just a few of the unique properties of water. And the first being, just to remind you again, the chemical formula for water is a molecule of oxygen bonded to an atom of oxygen bonded to two atoms of hydrogen. And remember that those are covalent bonds between the hydrogen and the oxygen, and that they are polar covalent bonds, meaning that there is unequal sharing. The electrons are actually held much more tightly or closely to the oxygen atom and away from the hydrogen atoms. And remember again, that leads to this partial negative charge on the oxygen and partial positive charges on the hydrogen. That polar quality causes this molecule of water to be what we call hydrophilic. Hydro means water, philic means to love, okay? So a hydrophilic means water loving, and water molecules indeed love other water molecules because of this unique partial positive and negative charge. If you imagine here, let me draw for you a second molecule of water with its associated partial positive and partial negative charges. And what I want you to notice here is that between this hydrogen I'm highlighting in yellow here and the oxygen of the adjacent water molecule, there is an attraction due to the partial positive charge of the hydrogen and the partial negative charge of the oxygen, such that we get the formation of something called a hydrogen bond between two adjacent molecules of water. The partially positively charged hydrogen is attracted to the partially negatively charged oxygen. Now, a hydrogen bond is not a true bond. In a true bond, there is either sharing or donation and acceptance of electrons. In this hydrogen bonding, we're not sharing or moving electrons around at all. This is simply an attraction between a partially positively charged area of one molecule and the partially negatively charged area of another molecule. What's interesting about these hydrogen bonds is this is what helps water stay in a liquid form despite the fact that you might keep adding heat to it. In other words, it takes an awful lot of heat to finally get the hydrogen bonds to break apart so that an individual water molecule will be released off into the air as a gas. And that is a very good quality to have, as I said before, because we wouldn't want water to boil very rapidly. If it did, then we would literally evaporate away as soon as we got too warm. Another quality of water is that it makes an excellent solvent. And a solvent is simply a liquid that has the ability to dissolve another either solid or liquid. So why is water such a good solvent? It has, again, to do with these partial positive and negative charges. If we take a salt molecule, sodium chloride, and we were to take that salt molecule and we were to plop it into water, something very interesting happens. Remember, salt is made of a sodium atom and a chlorine atom, and that when sodium chloride is put in water, it dissociates or splits apart, and one electron from the sodium is given away from the sodium and picked up by the chloride, so that we get a cation, or a positively charged ion of sodium, and a an anion, a negatively charged ion of chloride. Notice that there's a positive and a negative charge here, and these are full positive and negative charges because sodium has given up an entire electron and donated it to chlorine, and the chlorine has picked up that ion and become a chloride ion. Well, as you can imagine, the partial positive and negative charges of water are quite attracted to the fully positive and negative charges of sodium and chloride. And as you can see down in this picture here, the sodium cation right here with its positive charge is very attractive to the partially negative regions of the oxygen atoms in water. And those water atoms, when you drop sodium chloride in water, the oxygen portion of those water atoms will quickly surround that sodium cation to the point that it literally, even if it wanted to try to get back together again with this chloride ion, it could not. It physically can't get there because too many water molecules are surrounding it. It's the same thing with the chloride ions. Okay, the chloride ion has taken on an extra electron. It now has a fully negative charge to it, and the partially positively charged hydrogens in water molecules become very attracted to that fully negative charge. This is kind of like, if you think of it like Brangelina, like Brad and Angelina Jolie. You know, you could think of the sodium like Brad and Angelina's like the chlorine. Okay, and if you put these guys in the middle of a pool of paparazzi, a bunch of paparazzi that want to take pictures, those paparazzi are going to surround Brad on the one hand and surround Angelina on the other hand, and Angelina and Brad are going to have a hard time getting back together because there's so many camera men and women surrounding them that they can't get physically back together. Okay, so water is a really good solvent. It has these properties that make it a very good solvent. Now, I talked briefly on the last slide about hydrogen bonds. One thing I wanted to emphasize here is just how many hydrogen bonds one molecule of oxygen can form with other, one molecule of water can form with other molecules of water. So if I have this central molecule of water here with its associated partial positive and partial negative charges, and I look at other water molecules surrounding it, and I'll draw some for you here. We find that we can actually form hydrogen bonds, and I represent hydrogen bonds by a little dashed line here, forming between the central water molecule and 4 other molecules of water. Okay, and so one molecule of water forms hydrogen bonds with up to 4 other water molecules, and you can imagine that the amount of energy it takes to break these hydrogen bonds so that individual water molecules can, say, evaporate off into the atmosphere, it's quite a bit of energy. Okay, and again, that's why water stays liquid across such a vast array of temperatures before it becomes a gas. Okay, so water, we said again, is also a solvent because of that polarity, those partial positive and partial negative charges it has. Just to let you know on a little terminology here, a solution is made up of a solvent, like water, some liquid, plus a solute, and that's the substance that becomes dissolved in the solvent. And the two of them together, solvent plus solute, gives a solution. Now, lots of things dissolve readily in water because they have either partial positive and negative charges themselves, or they have fully positive and negative charges themselves, and so they're attracted to the partial positive and negative regions of water. In other words, they too are hydrophilic. They like water. They hang out well with water. On the other hand, there are some substances that do not dissolve well in water, and oils are a good example of that. If you are making a salad dressing and you combine, let's say, water with, I don't know, olive oil, for example, you'll notice that when you pour the olive oil into the water, what happens? Well, the olive oil stays on top and it does not dissolve with, mix with, or become part of the water. They stay separately. The reason for that is oils are what we call hydrophobic. Phobic means to fear, so these are water fearing. And the reason why oils do not mix well with water is oils have no partial positive and negative charges, and they have no fully positive or negative charges. So they don't associate well with water with its partial positive and negative charges. Okay, so oils are non-charged molecules. They don't have polarity. They don't have partial polar, partial charges to them. What's interesting about detergents is they have the ability to force things like oils to become dissolvable in water. And here's how it's done. I mean, if you think about it, if you have a sink full of water and you put some greasy pans in there to wash them, all the grease comes off the pans and bubbles up to the surface of the water and floats on top. Well, what happens when you drop a couple drops of detergent into that sink full of oily water? If you notice, the oil breaks up very rapidly and disappears and is no longer floating on top. That detergent has a very unique property to it. Detergent is made up of one region, in this picture here, that is hydrophilic, meaning water-loving, meaning it has those partial positive and negative charges that are attracted to the partial positive and negative charges in water. And it has another region down here, the tail region, which we say is hydrophobic, water-fearing. Well, it turns out the hydrophobic or water-fearing portion of this detergent molecule is a lipid or an oil itself, and it's very attracted to other things that are also hydrophobic, like the oil. Whereas the head of this detergent, which is hydrophilic, is very attracted to water. So the hydrophobic tail of this detergent molecule is very attracted to the oil and associates closely with it. And at the same time, the hydrophilic head of this detergent molecule is very attracted to water, and it associates closely with water. So in other words, detergent is almost like it's like a bridge molecule. It bridges a connection between the water molecules and the oil molecules because it contains both hydrophilic and hydrophobic regions. When a molecule has both hydrophilic and hydrophobic regions to it, we say it is amphiphilic. Amphi means both. Think of an amphibian. It can exist both on land and in water. Think of people who are ambidextrous. Okay, ambi and amphi are basically the same thing. They mean both. Somebody who's ambidextrous can use both hands. All right. The last thing I want to talk about is a little bit about pH, because it's a topic we come back to time and time and again in this class, and if you go on into anatomy and physiology classes, you'll also encounter the topic of pH because it's very relevant to body chemistry and physiology. What is pH exactly? Well, pH is basically, it's a measure of how many hydrogen ions are present. Okay, it's a measure of how many hydrogen ions are present. If we look at water, H2O, water has what we call a neutral pH. And if we have a scale of pH values, and that scale runs from 0, which is absolute acid, all the way up to 14, which is absolute basic. Right in the middle at 7 is neutral, and that's what water is. Okay, so the lower the pH number, the more acidic it is. Okay, acid means it has a lot of hydrogen ions present. So the lower the pH, the more hydrogen ions are present and the more acidic it is. The higher the pH, the fewer hydrogen ions are present and the more basic the solution is. Okay? Now, if we look at water, and we were to take a bunch of water in a flask and use a camera that could actually see molecules, if one existed, we would see that if we took a snapshot in time, that water molecule, there were a few water molecules in that flask that have dissociated into a hydrogen ion and a hydroxy ion. Hydrogen ion is just the hydrogen itself without its electron, and a hydroxy ion is an oxygen and a hydrogen bonded together with an extra electron, so it has a negative charge. The number of hydrogen ions present, again, remember, indicates how acidic that solution is. pH, if you want to get into all the fancy math here, how we calculate pH is we look at the concentration of hydrogen ions, and we use square brackets like this to represent concentration. And if we take the negative log of that, that gives us the pH. So water, if we look at it at any snapshot in time, we took a picture of it, about 1 times 10 to the negative 7th of all the water molecules in that flask, or about 0.1, 2, 3, 4, 5, 6, 7. Okay, a 1 with 6 zeros in front of it. So really, really tiny amount of those water molecules have actually dissociated into hydrogen ions and hydroxy ions. If we take the negative log of 0.00000001, the negative log of that value is the number 7. And that's where we get the neutral value pH. Okay, so again, just to summarize, hydrogen ion concentration, if you take the negative log of it, you get a number that ranges from 0, which is highly acidic, all the way up to 14, which is completely basic. Okay, so the more hydrogen ions you have, the pH value is lower, and the more acidic the solution you have is. Okay, and this diagram gives you it gives you an idea of lots of different substances at different pHs, so you can kind of understand the relationships. Black coffee, for example, is much more acidic than household bleach, which happens to be quite basic. All right, our last slide here is just to briefly remind you again that among all the different types of atoms and molecules that are essential and critical to your existence are a lot of different minerals and gases that we find in the body. Gases like nitrogen, which makes up more than 70% of the air that we breathe, oxygen, carbon dioxide, water vapor are all gases that we breathe in and out all of the time. Or minerals, things like copper and phosphorus and potassium, manganese, zinc. Those are all examples of different types of inorganic elements that are absolutely critical to the functioning of our body. A lot of those minerals are what we call trace minerals, meaning that only very, very tiny amounts of them are found in your body. But it turns out that if you didn't have them, there are many different types of enzymes and activities that happen inside your body that would not be able to proceed without the presence of those different minerals. So they are really, really important. If you continue on into anatomy and physiology, you'll learn plenty more about that. I'm going to wrap this up as the end of our small molecules lecture. If you want more information about water and its properties, make sure you look in your textbook. And in fact, I'd suggest you do look in your textbook and not just rely only on lecture. This is just like any other class. You have to get through lecture, but you also need to be reviewing with your textbook so you're adequately prepared for your first test. And I will see you in class.